Okay, this is Mr. Martin. These are the video notes for math analysis for section 6.4. We're going to be talking about dot product of two vectors, and you may have seen this in physics. So basically dot product is a vector operation, just like we did addition of vectors and how we did multiplication by a scalar with vectors. When we did addition and multiplication, the answer to both of those types of problems was also a vector quantity. The difference here is that when we do the dot product operation, our final answer is going to be a scalar. So it's simply going to be a number. Okay, so make sure you understand this. Answer will be a number. Okay, and then as always, as we go through the video, if you have questions, make sure you write them down in the margin of these notes, and then ask me next time you see me in class. Also, if you haven't downloaded the notes that you're looking at here in the video, make sure you go back to my website and download those. They're on the flipped video page for Math Analysis Semester 1. And you'll see the Chapter 6 stuff is right up at the top. There's only a couple of links there right now. So make sure you print those out and use them when you are going through this video. Okay, so the definition of a dot product, if we've got vector u and vector v, u dot v is given by u1 times v1 plus u2 times v2. So again, we're really doing nothing more complicated than adding and multiplying. So we've got the x components here, and we've got the y components here. We're multiplying those together, and then simply adding them up to get a scalar. Again, it's just a single number. Certain properties of dot products that we may use while we're working on these types of problems. So make sure you look these over, and if you have any questions, they're very similar to the ones that we use for algebra, so it shouldn't be anything too crazy for you. But again, look those over and make sure you ask me any questions that you may have. Alright, so moving on to the first example, we want to find the dot product of the two vectors v and w, so we're going to do v dot w. So we're going to take the two x components, so that's 2 and negative 3, and then we're going to add that to the product of the two y components, so that's negative 4 and negative 5. So we get negative 6 plus 20, and final answer is 14. Just keep an eye on me if I make any mistakes. Just send me an email or correct me in class. So you see we did the dot product operation and we got a single scalar number, which is 14. Alright, so if you want to pause the video and go ahead and work out part B, when you start it back up you'll see the solution and you can compare your answer. Otherwise you can keep the video rolling and it will just pop right up. Okay, so let's compare answers. I've got negative 19 here. You see I multiplied 5 and 6. Those are the x components. I multiplied 7 and negative 7. Those are the y components of each vector. And then added them, in this case subtracted them, to get negative 19. Alright, so moving on. Example 2, we want to find u dot w times v. So if you're thinking ahead, we know that u dot w, this is going to be a scalar, and then we're going to multiply that by vector v, so our final answer should be a vector quantity. So let's do u dot w first. So we've got 3 times negative 3 plus 3 for the y component here, and then w, we want the y component there, so that's negative 5. So I've got negative 9 plus negative 15, so we get negative 24. So now I'm going to do u dot w times v, so that's going to be negative 24 times 2 comma negative 4, and I get negative 48, comma, positive, let's see, that's 1696. Hopefully I did that right. I'm doing these in my head. But again, if I make any mistakes, make sure you let me know through email or next time you see me in class. Okay, so, just work it out piece by piece. Try and think about what's going to be a scalar, what's going to be a vector. And let's move on to part B of example 2. So for part B, I've got 2 times u, the dot product with w. So again, our answer here is going to be a scalar because really we're just doing a dot product. So we're doing the dot product of twice u times w. So I'm going to find 2u first. So that's going to be 2 times negative 1, negative 3. So that gives me negative 1, negative 2, comma, negative 6. And then I'm going to do the dot product with w. So I'm going to do negative 2, that's the x component of 2u, times 6, which is the x component of w. And then I'm going to do the y component of 2u, so that's negative 6. I think I may have said something backwards, but I think the work here is right. And then times the y component of w, so that's negative 7. So I've got negative 12 plus 42 to give me 30. Again, we have a scalar answer in this case. Okay, moving on to example 3, we're actually going to use one of the properties of dot product here. So let's read the problem here. We have the dot product of v with itself is 32, and we just want to find the magnitude of v. So if we scroll back up here, we're going to look here at this fourth property where it's v times v is the magnitude of v squared. So let's go back down here, and we've got v dot v is equal to the magnitude of v squared. Okay, so we know the dot product of v in itself is 32, so the dot product of v with itself is going to be 32. So if I take the square root of both sides, then I end up with the magnitude of v is going to be the square root of 32, which is 16 times 2, so 4 root 2. And there's our answer. This would be the magnitude of v. So we don't know what the components are, but we do know what the magnitude is. Again, just an example of using one of our properties of dot product. Okay, moving on. Angle between two vectors. So there were actually some problems in the last section on this, and I think they asked you to find the angle between vectors using the law of cosines. So what we've got here is another formula. We're not really going to derive it, but it is in your book if you want to find it. I'm sure you can find a derivation of it online as well. So basically, if I have two vectors, u and v, so here's u, and if I have v over here, then the angle between the two vectors would look like this. Okay, and it's always going to be the angle less than or equal to 180, so keep that in mind. So if you notice here, we've got the cosine of theta. So at the very last step, we're going to have to do the cosine inverse. And then we've got the dot product in the numerator, and we've got the product of the magnitudes in the denominator. And before we move on to an example, let's take a look. We've got the dot product up here. So if we rearrange this and solve it for u dot v, we get another form of dot product which may come in handy, and we'll actually do some examples using this one instead. So instead of doing the product of the x components plus the product of the y components, we could also do this if we know this information. Okay, so moving on, we're going to make a sketch of the two vectors and then calculate the angle between them. So we just need a quick sketch. It doesn't have to be too accurate. So I'm going to estimate. We've got negative 1, 3. So I'm going to estimate that somewhere down here. And then I've got 5, 7. So I'm going to estimate that somewhere over here. So here's V. Here's U. And I want to find the angle between here, theta. Okay, so I know that the cosine of theta is equal to u dot v over the magnitude of u times the magnitude of v. So I'm going to do some work over here on the side. I'm going to find u dot v. So that's going to be negative 1 times 5 plus 3 times 7. So that's negative 6 plus 21, which gives me 7, having some trouble here, 15. So that's going to be the numerator. And then I need the magnitude of u. So that's going to be the square root of negative 1 squared plus 3 squared. So that's the square root of 10. And I need the magnitude of v. So that's going to be the square root of 5 squared plus 7 squared. So that's the square root of 25 plus 49, which is the square root of 74. Okay, and don't worry about simplifying these because we're just plugging them back into the formula here. So I've got dot product, which was 15, over the product of the magnitude, so that's square root of 10 times the square root of 74. And then we're going to find that, and at the end we're going to do the cosine inverse of our answer, and hopefully you come up with about 56.5 degrees. So there's a fair amount of work here, but again, nothing is terribly difficult to figure out. So let's go ahead to example 5. We want to find the dot product given the magnitude of u is 6, the magnitude of v is 15, and the angle between the vectors is 2 pi over 3. So again, we can use this other form that we have here. U dot v is the product of the magnitudes times the cosine of the angle. So u dot v is equal to the magnitude of the vectors multiplied together times the cosine of the angle. So I've got 6 times 15 times the cosine of 2 pi over 3, and since this is one of our special angles, I've got 6 times 15, 2 pi over 3 is in the second quadrant, and I want the cosine, so that's going to be negative 1/2. So let's see, that's going to be negative 3 times 15, so I get negative 45. So that's the dot product of u and v. Okay, so very briefly, moving on to the last concept here. Orthogonal, it's a very fancy word, and really it's just another word for perpendicular, or vectors that meet at a right angle. And the interesting thing about this is that if you do the dot product of orthogonal vectors, it turns out to be 0. So you could find the slope of the vectors and see if they're opposite reciprocals, which is use slope. I gave you the answer to that question. If they're opposite reciprocals, then they would be orthogonal, or you could just do the dot product of the two vectors, and if it turns out to be 0, then you know that they're perpendicular or orthogonal. So a little bit of vocabulary there, make sure you know that. Again, if you have any questions or weren't sure about any of the example problems, or if I made any mistakes, make a note of that, and make sure that you ask me next time you see me in class. We'll see you next time.